my role right now is as one of the faculty members involved in LIGO lab at MIT. And my research over the last few years has been on experiments to make improvements to LIGO detectors. And that's sort of kind of been a little bit my trajectory over the last decade, is at every point I'm chasing the next best detector. But I'm an experimentalist, and I build experiments that are all targeted towards making improvements to gravitational wave detectors, and LIGO in particular. You know, at some point, the way I like to think about it is, we don't know what's out there in nature. All we know and can control is what's the best instrument we know how to make. And so I just work on making better and better instruments with the hope that sometime they'll be good enough to catch everything nature is trying to tell us. So if you want to put it in the very simplest terms, the measurement we want to make is, we put mirrors 4 kilometers apart, and we try to measure relative changes in their distance of 10 to the minus 18 meters. How do you do that? Well, in principle, you actually only need to do 2 things. The first thing is, you have to make these mirrors really, really still. Everything else on the planet is trying to move them by more than that 10 to the minus 18 meters. So we have a lot of the technology that goes into building LIGO is shielding the mirrors from external forces, making their motion be very small. So there's a lot of vibration isolation and a lot of control of the thermal fluctuations. You know, we all jitter from thermal energy, and we have to control that. You do that, you do it successfully, and it would be kind of useless if you didn't also have a way of measuring those tiny motions. And that's where our laser light comes in. Our laser light is the meter stick that we use. And that's how we probe these tiny motions. Lasers are actually fantastic meter sticks, but they're not perfect. So imagine I gave you a ruler, and I said, measure the length of this piece of paper. It'd be easy, you'd measure it. But imagine now I gave you a ruler where the tick marks on your ruler jitter around a little bit. So you measure your piece of paper, you make a measurement, you measure it again, it's a different number. And that's what laser light does to us. It has quantum fluctuations on it. And what we try to do then in our labs with our experiments is to try to reduce those fluctuations. It's simply put, we try to reduce the amount of jitter on the tick marks of our meter stick.